Hi students, I am Sheeba, EC department from Emmanuel Arasar JJ College of Engineering. Today we are learn about some of the applications of operational amplifier. The applications of operational amplifier are sign changer, scale changer, phase shift circuits, voltage follower. First, we can see the introduction. In linear circuits, the output signal varies with the input signal in a linear manner. Examples of adder, subtractor, voltage to current converter, and current to voltage converter, instrumentation amplifier, analog computation, power amplifier, etc. This is the another class of circuits with a highly non-linear input to output characteristics. Examples are rectifier, peak detector, clipper, clamper, sample and hold circuit, log and anti-log amplifier, multiplier, etc. These non-linear circuits are very useful in industrial instrumentation, communication, and general signal processing. The operational amplifier or op-amp was originally developed in response to the requirements of analog computer designers. An operational amplifier is a high gain direct coupled amplifier. First we can see the sign changer. In the ideal inverting amplifier, if RF equal to R1, then the gain is equal to minus 1. Thus the magnitude of output is same as that of input, but its sign is opposite to that of the input. V0 equal to minus Vin for RF equal to R1. This circuit is called sign changer or phase inverter. Figure shows the basic inverting amplifier configuration using an op-amp with input impedance Z1 and feedback impedance ZF. The closed loop, the gain is minus ZF by Z1. The closed loop voltage gain is minus ZF by Z1 if are equal in magnitude and phase, then the closed loop voltage gain is minus 1 and the input signal will undergo a 180-degree phase shift at the output. Hence, such a circuit is called a phase inverter. Next, the scale changer. In figure, the basic inverting amplifier, if RF by R1 equal to K, then gain equal to minus K, where K real constant, and the scaled output is available at the output. Usually, in such applications, ZF and Z1 are selected as precision resistors for obtaining precise and scaled values of input voltage. Next, we can see the phase shift circuits. The phase shift circuits produce phase shifts that depend on the frequency and maintain a constant gain. These circuits are also called constant delay filters or all pass filters. The constant delay refers to the fact that the time difference between input and output remains constant when frequencies change over a range of operating frequencies. There are two types of phase shift circuits. The Two types of circuits are lagging phase angles, that is phase lag circuit, leading phase angles, that is phase lead circuit. First one is phase lag circuit. Figure shows the phase lag circuit constructed using an op-amp connected in both inverting and non-inverting modes. To analyze the circuit operation, it is assumed that the input voltage Vi drives a simple inverting amplifier with the input applied at negative and positive terminals of op-amp. It is also assumed that inverting gain is -1 and non-inverting is 1 plus Rf by R1 equal to 1 plus 1 equal to 2, since Rf equal to R1. For the circuit shown in figure, V0 of j omega equal to minus Vi of j omega plus 2 into 1 by 1 plus j omega into RC Vi of j omega. Therefore, V0 of j omega equal to Vi of j omega minus 1 plus 2 into 1 by 1 plus j omega into RC. The relationship between output and input can be expressed by V0 of j omega by Vi of j omega equal to 1 minus j omega into RC divided by 1 plus j omega into RC. Phase lag circuit, the relationship is complex as defined by equation, and it shows that it has both magnitude and phase. Since the numerator and denominator are complex conjugates, their magnitudes are identical and the overall phase angle is equal to the angle of numerator minus the angle of the denominator. The phase angle is then given by theta equal to minus tan inverse omega into RC minus tan inverse omega into RC equal to minus 2 tan inverse omega into RC. Here, when f equal to f0 in equation, the phase angle theta equal to minus 90 degree. The board plot for the phase lag circuit is shown in figure. Next, we can see the problem. Determine the phase angle and the time delay for the circuit shown in figure. The frequency of 2 kHz, assuming R1 equal to 20 kilo ohm, R equal to 39 kilo ohm, Rf equal to R1 and C equal to 1 nanofarad. The circuit is a phase lag circuit, means f0 equal to 1 by 2 pi RC. So substitute the values, we can get 4081 Hz. The phase angle is 2 kHz, means theta equal to minus 2 tan inverse of 2 into 10 power 3 by 4081 equal to minus 52.2 degree. Then Td equal to 1 by f into theta by 360 degree. Substitute the values, we get the answer 72.5 microseconds. Phase lead circuit. The phase lead circuit is shown in figure, in which the RC circuit forms a high pass network. The output voltage is derived and expressed by V0 of j omega equal to minus Vi of j omega plus 2 into j omega RC divided by 1 plus j omega into RC Vi of j omega. V0 of j omega by Vi of j omega equal to minus 1 plus j omega into RC divided by 1 plus j omega into RC. Theta equal to 180 degree minus tan inverse of omega into RC minus tan inverse of omega into RC equal to 180 degree minus 2 tan inverse of omega into RC. When the frequency approaches 0, the phase angle approaches 180 degree. As the frequency is increased, the leading phase decreases and it finally approaches 0 at high frequencies. Hence, the above equation can be written as theta equal to 180 degree minus 2 tan inverse f5 f0, where f0 equal to 1 by 2 pi into RC. Next, we can see the voltage follower. If R1 equal to infinity and Rf equal to 0 in the non-inverting amplifier configuration, then the amplifier acts as a unity gain amplifier or voltage follower. AV equal to 1 plus Rf by R1 or Rf by R1 equal to AV minus 1. Since Rf by R1 equal to 0, we have AV equal to 1. The output voltage is equal to the input voltage both in magnitude and phase. In other words, V0 equal to Vi. Since the output voltage of this circuit follows the input voltage, the circuit is called voltage follower. It is also referred to as a source follower, buffer amplifier, isolation amplifier, or unity gain amplifier in practice. Thus, the voltage follower can be used as a buffer between a high impedance source and a low impedance load for impedance matching applications. Thank you.